So the website will be the seeclab.com. So seeclab.com. And then you go to teaching and 438. And then you go down to there's the password. I just changed it today. It's small a 438 and then capital A 438. So that will just change today. And then I will have everything related to the class on the website accessible. So hopefully it will be in an organized fashion so that you don't get lost. So we will have, the course logistics will be at the top, the syllabus, the lecture schedule, the lab schedule. I think Wissam already sent you the lab schedule for the semester by email. Ah, you didn't? Was it only to me? Okay, sorry. But anyway, it's up on the website. We'll go through now. All the slides for the slide material is here. I will use a combination of slides and writing on this board. So I will typically have utilize a combination of writing on this board as well as on the slides. So it will be, there's stuff that's not on the slides that we will cover. These are the main chapters that we will cover in the textbook. We, maybe up to chapter 5, maybe we will cover everything in the chapters. And then chapter 6 and 8, we will cover, maybe half of this, half of that chapter. So that's the current plan. The lab manual is here. I may update it based on feedback from Wissam, but this is the latest lab manual that I have. 5 labs, I think. I mean, I will check the schedule that Wissam sent. I may have something. I may have missed something. I will have all the lectures up here. So all the links to all the lecture videos will be up here. As soon as we, finish this class, for example, you can go into the website. You'll be able to click and watch the lecture. The homeworks are up here. They don't have due dates at the moment yet. So I will update them with due dates. So the assignments are all from the textbook. Again, the homework will not be graded for accuracy as such. We'll go through the syllabus. It will be the same policy that I was using in 325. So we will have quizzes on the homework during the lab. We will not be grading the homework as such. You will get credit for submitting the homework and doing it in a legitimate fashion. So not chicken scratching on the paper and stuff like that. So points will be deducted for that. If it looks bad, you will lose points. Yeah. So I will go through that. And then I have a lot of supplementary. So the homework solutions will be emailed to you after the submission deadline. There's a lot of supplementary material that we have here. The full equation sheet for everything we will cover in class is here. So when you do your homework, utilize the equation sheet. So it covers all the equations in all the chapters. I think if you've taken a class with me before, it's useful. So I would do the homeworks with the equation sheet, so that if you find something that is not on the equation sheet, for example, let us know, so we can update the equation sheet. But and this is the equation sheet that you will utilize on the exams. So it's best that you utilize it to do your homeworks. Yeah. I have some previous solved exams on here, so a bunch of solved exams from previous years up here as well. The rest of the stuff will be things that we will utilize. So, Fourier series sheet, and then some waveform drawings that we will utilize throughout the semester. Some data sheets. Again, power electronics. Very similar to electronics. I think, like the 325 course, you should be able to look up a device look in the device data sheet and understand certain properties of the devices. And in power electronics, it's not just devices; it's devices as well as reactive elements, meaning capacitors and inductors. And we will figure out how to size things like that. So, for example, the filter at Qatar Steel, why is it there? How do you size a filter like that? So this is something we will cover in the class. A transformer, we will cover a little bit about transformers in the class, even not as much as 459 class, but a little bit that is useful, or a little bit that is relevant to the 438 class. So a lot of these data sheets we will go through during the semester. So while we are working on something, I'll open up the data sheet. So, but I have them all up here for you for for convenience. Yeah. So this will be the sort of the website that we will utilize all the time. So it's hopefully it will have everything you need. Yeah. Yes.
What's the password?
Small a 438, capital A 438.
Uh,
Small a.
small A.
Small a. Okay. Let's skim through the syllabus. You got it? Okay. So we'll skim through the syllabus. So, so the course is about power conditioning. So what is power conditioning generally? I mean, what is really the main theme of this course about? I mean, can somebody tell me what is power conditioning? What do you mean by what would I mean by the words power conditioning or power conversion?
You have a power source that's rated at some voltage and some current at some shape, AC, DC, whatever, and you want to convert that to another shape that you want.
Sure. So that's exactly what we're going to be studying, and depending on your source and load, you will be plugging in different types of circuits in the middle, right? So, and these different circuits, there's no right answer as well. So there may be 5 different alternatives to what you can plug in between a source and a load to satisfy the source's requirements and the load's requirements. I mean, the source's requirements, actually, yes, there will be not a single solution, but there will be a better solution to utilize, for example, when you care more about efficiency. There will be a better solution when you care more about cost. There will be a better solution when you care more about size. There will be a better solution when you, for example, have a high ambient temperature. There will be a better solution when you are worried about electromagnetic noise. You have a very precise measurement that that you have to create very close by to this power converter, and this measurement will be disrupted by any electrical noise. So by meaning electrical noise, meaning changing electric fields or changing magnetic fields. Changing electric fields and changing magnetic fields, what do? They induce currents and voltages in a wire. If you have a changing magnetic field and you put a wire in a changing magnetic field, you will induce a voltage at the terminals of this device, of this wire, and if you close the loop, you'll have current flow, right? So a piece of wire that's close by to a changing magnetic field is something that is going to cause noise. Maybe it's a small amount, but how much can you tolerate? If you are measuring something in the nanovolt range, then you cannot tolerate much, right? So what power supply do you utilize in this application, right? So in this course, we're not going to be studying circuits like, in 325, you were studying amplifiers. The main objective of the amplifiers you were studying in 325 is to do what? Take a measurement signal and be able to send it through to an analysis electronics, whether that is analog or a digital computer, by amplifying it, filtering it, doing something to it that, in the frequency domain, right? So you would maybe take your signal and then filter it, and then you amplify it. You would have a gain to the amplifier, and then there would be a frequency response to the amplifier. So that was mainly 325. So here we don't do that. Here our objective is to, in 325, the op-amp had terminals, power supply terminals, right? These power supply terminals were what? Plus minus 12, plus minus 5, 0 to 5, 0 to 3.3, 0 to 1.8, whatever it was, whatever it is. The objective here is to figure out how to develop a power converter or select a power converter that's for a suitable application. And these power converters, they range in power rating from, nanowatts, microwatts. That if you talk about the smartwatches, the idea there is to design something that is going to consume as low as possible the amount of power, so that you can preserve battery life, right? So that's the objective of something that is battery operated, for example. Versus when we talk about Qatar Steel, for example, they are supplying a big arc furnace. So how do you supply a big arc furnace? Is there a power supply required to be placed in such a system so that you can supply. The RAS gas powertrains, the compressors that are used to compress the natural gas, are driven by large motors. These large motors require speed control. You do not just run them off the line. Some of them run off the line, but the large LNG compressors, they do not. They are all driven by a motor that has to be controlled in speed. So this controlled speed is, from a power converter. Whether you call it a motor drive in that case, or you call it an inverter, but at the end of the day, it's a power converter, right? So there are many names for a power converter. We will talk more about the different names people give power converters, and why people give them these sort of names. But
So what do you mean off the line?
off the line meaning you take a motor and connect it to the three-phase AC supply, like a power system. In the 459 class, we had motors in the power system. These were directly connected to the three-phase power. But if you want to control their speed, you cannot, right? You have to connect it to a power converter that will change, voltage over frequency ratio with a certain amount, right? If you took 338, you know that you cannot. If you want to change the speed of a motor, you have to maintain the voltage over frequency ratio to be a certain value. If you want to maintain voltage over frequency ratio to be a certain value, it means you have to change the voltage magnitude and frequency. And you do that with a power converter, right? So these are and in that case, the power converter can be called an inverter. And we will study that in chapter 8, for example. Inverters will be studied in chapter 8. So power converters are, like the big name that encompasses many different applications, and we will talk about the different applications shortly. So, as I said, so the only prerequisite for this course is really 214. So 214 is a very important course, and you will do a lot of circuit analysis and stuff that's important in this course. Yeah. The textbook, as I said, is the Daniel Hart book. There are many textbooks out there on power electronics. They're very useful if you want to solve more problems. So I would recommend looking at them. But really, if you concentrate on doing, working with this book and the problems in the homework, etc., you should be fine. There's a lot of waveform drawing in this class. So this is something that some students sometimes find difficult, I would say. So we will be drawing a lot of the waveforms. So I will spend a lot of time drawing waveforms. That's why in the supplementary material you will find, for example, just a blank sheet with the three-phase AC waveforms, a single waveform. We will, the idea is we would like to convert power to a different form. So you have power in a certain fashion, and you want to maybe chop it up, or maybe turn it on for a certain period of time and then off for a certain period of time. So how do you do that? What circuits are used to do that? And then what does the waveform look like? And what is the effect on the grid, right? So these filters that the Qatar Steel guys have, it's because the load is affecting the current shape in a certain fashion. The utility does not like that. So they tell Qatar Steel, okay, you put a filter. Right, so it's because you have a load that is distorting the current, and power electronics distorts the current. By definition, all we're doing is chopping up the voltages and currents. So we no longer have a nice sine wave anymore. The utility likes nice sine waves, and the utility likes unity power factor. What is unity power factor? What does unity power factor mean?
When you're not using any reactive power.
Okay, so what do the voltage and current waveforms look like in that case? They're the voltage and current are in phase. They're sinusoidal and in phase. In that case, you have unity power factor. So, which in this case, you're only sending real power from the utility. Okay, for those who took 459, we know that this cannot happen. Right, that all your cables look like inductors. So inductors, tend to utilize reactive power. Reactive power is this power that is not producing torque, not producing light, not producing energy, right? But it's power it's current that goes back and forth, that is flowing in the conductors of in your conductors, that is required to do what? It's required to set up magnetic fields. whether you're trying to set up the magnetic field in the transformer, whether you're trying to set up the magnetic field in the motor, you are required to set up this magnetic field. This magnetic field is not producing power as such. It's when you set up the magnetic field in the transformer, what happens? You're linking the primary turns with the secondary turns of the transformer. The actual power is being transmitted through the windings, but there is no, this reactive power, this magnetic field remains in the transformer. It's not something that you transmit, to the next step or to the next load. It's a magnetic field required for the transformer to operate. Motors are the same thing. In an electric motor, you are required to have the rotor run after the stator, for example. They need to work together. So they are working together through the magnetic field. So there is a magnetic field required to link the stator and the rotor. This magnetic field is developed using reactive power. So anytime you have a magnetic field, you know that there is reactive power involved. Yeah. So reactive power is there. You will have to have it. The generator likes to actually produce some kind of reactive power. You can ideally operate with unity power factor, but when we took 459, we saw that actually that is not something that you want to do to a generator, because electrical generators tend to limit the capacity of the electrical utility if you're operating at unity or leading power factor. So the utility likes to operate with some lagging power factor, small amount of lagging power factor. So it will dictate. It will tell Qatar Steel, it will tell any other RasGas, it will tell all the industries I would like to operate with typically 0.9 or 0.95 power factor lagging. So we will talk a lot about waveforms and power factor. It will be a lot of review for those who took 459, just the definition of power. That will be a small part of the course, and then we will after going through the syllabus, we will get into some applications and understand some draw some block diagrams talking about some applications in power electronics. For you to convert power, like 325, we studied mainly the MOSFET and the BJT and the diode. Actually, there's not too many more type of devices. We took the MOSFET and we called it a power MOSFET. We took the BJT and merged it with the MOSFET and called it an IGBT. And we will talk more about that. And then we took the diode and we call it a power diode. And then we took a diode and added some little bit of control to it, and we called it thyristor. So we will study all of these different devices. We will not get into the physics of the devices like we did in 325. We will study them more from an application perspective. So in 325, you study the electrons, the holes, the channel formation, blah blah blah. We don't study that here. I will just briefly put up the IV characteristics of the devices that you studied in 325, just as a review for those who took 325. For those who didn't take it, that's not a requirement. It's just for you to just to get a feel of voltages and current in the devices. And then we will sort of tell you, okay, in power electronics, we don't use all of this. We just utilize very limited operating characteristics of the devices that you studied in 325. So we will utilize most devices as switches. In 325, you utilize the devices mainly as what? Amplifiers, right? So in the saturation for the BJT or in the linear mode for the MOSFET, you were utilizing the devices as amplifiers, right? You were building amplifiers with the devices. Here we are not. We're going to try to use them as switches. So the switch means what? It's either off. Off means cut off. Right? If you remember your 325, it's the cutoff. It means cutoff. When the devices are fully on in that case, we will only operate in a very limited zone of the characteristics of the device. So in the MOSFET, we will only operate in the triode zone, and BJT or IGBT in the power device case, we will operate in what we call saturation in that case. So you'll only operate on very limited areas of the characteristics, the voltage current characteristics that you studied in 325. So we will review those for those who did not take 325. It's not a big deal yet. Then we will move on to, as we said, talk about power, but talk more about power quality. So we'll find ways to quantify power. So talk about RMS, harmonics. How do you quantify harmonic distortion? So we added a filter. Qatar Steel guys added a filter. Why? It's because they were creating distortion. They were distorting the current. The current was no longer a sine wave, or the voltage was no longer a sine wave. So how do you quantify distortion? There are, it's a term called total harmonic distortion. And then other terminology to specify waveforms like crest factor, etc. We will spend some time on those so that we can utilize them. It's nothing new. It's just okay. The peak value over the average value, the peak value over the RMS. We will call it different names. It's just jargon that power electronics people will tend to utilize, or power people will tend to utilize. And then here points 4 and 5 we'll be talking about certain family of converters. So here this certain family of converters will be the AC to DC converters. So we will study a set of AC to DC converters, meaning I have an AC outlet here provided by the utility. I would like to charge my phone. My phone battery is a 3.7 volt lithium battery. So I need to charge my laptop from the outlet. So I need to go from AC to DC, right? So what is the voltage and frequency of the outlet here? What? 50 hertz, and the magnitude is 240 volts RMS. It's typically what we have here in Qatar. Yeah. So RMS, right? And it's RMS. I want to convert that from 240 volts RMS, 50 hertz. I would like to convert it to 3.7 volts DC. Right? So how do you do that? So we will study one family of converters that allows us to do something like that. Again, we will not study. There are tons of other ways to do it versus what we will be studying. But we will study one way of doing it, and then you can find if you take more advanced courses in power electronics, you will study different ways of doing the same thing, right? But different ways can be more efficient. Different ways can be more utility friendly, meaning less distortion to the current on the utility side. So less requirement for filtering, for example, on your side. So these will be more advanced converters that maybe cost more, maybe more complicated to develop, maybe more difficult to develop at high power. Maybe low power can be okay. So again, that's power electronics. Basically, we're looking at topologies. It's many different topologies that do something. So that's the AC to DC conversion. That's one family we will study. Then in point 6 here, we talk about AC to AC conversion. So sometimes you have like a light dimmer. Light dimmers, for example, that you may have in your house. A switch you turn around, right? The switch you turn around is changing the light intensity. How is it doing that? One way to do that is an AC to AC converter. You have an AC voltage of a certain value and a certain frequency. Regular incandescent lights, if you change the value of the voltage, not its frequency, if you change the value of the voltage that you are applying to the incandescent light bulb, the intensity will change. That's for the incandescent bulb, but is it the same for any other bulbs? No, not necessarily. Bulbs that require a power converter, like fluorescent lamps, it's not the case with a fluorescent lamp, right? That is actually a full power electronic converter that is used to run the fluorescent lamp. So you can do that with an incandescent bulb, for example. Another main application for the workhorse of point 6, which is the AC voltage controllers, is something you may have seen if you've interned in your RASCAS and you were interested in the electrical system a little bit more than the instrumentation system. So you may hear the word soft starter. So soft starter. Have you heard? Like a star delta is one form. Why do we use a star delta?
Because basically at the start there's a rush of current. That's what usually happens when motors start. There's a rush of current, and you don't want that because it's not good for the motor. Something will burn inside. So you use the star delta to gradually start the motor.
Actually, it can be okay for the motor, but the utility doesn't like that, or it can be okay for the utility and the motor doesn't like that. But so it's motors, induction motors start with a huge inrush current, so maybe 5 to 6 times the rated value. Typically, they will be designed to tolerate that. But sometimes what happens is the supply, your source, does not like that. You're connected to, you're one motor in a big industrial facility, right? If you are drawing a large amount of current, what does that mean from a voltage drop perspective? High current, higher voltage drop. Higher, because again, assuming you have the same cable, of course, in the middle between your source and your load, then if you draw a higher current, you're going to have a higher voltage drop. Higher voltage drop is something that some other piece of equipment may not like, right? I mean, there's some other sensing device may be rated for a certain value of voltage input. If you decrease the voltage beyond a certain point, maybe that device will disconnect, or maybe that device will give wrong results, right? So motor starting studies are very important when you're going to design, for example, an expansion to your industrial facility, or you're going to design a new industrial facility. You would have to take into consideration the motor starting. It's called a motor starting study. Why you would put these motors and connect them and see what happens when you start these motors without a power converter in the middle, right? Because there's always a solution. For you to put the power converter, you will solve the problem. But of course, it's cost, right? Ideally, you would like, okay, fine. Ideally, I would like to buy a motor that is going to be running at a certain speed for my LNG compressor. I don't want to put extra cost in the middle. It's not just cost. It's anything you put will require maintenance, require cost, will break down, blah blah blah, right? So then okay, you really don't want to put something, but if you have to, you will, right? And what you will put in there is a power converter. Okay, what kind of power converter will you put in there? Well, it depends. Depends on the application in that case, right? So one of the most important power converters that are put in a utility or an industrial application is a soft starter. It's called a soft starter. These soft starters are AC voltage controllers. So what they do is they control the AC voltage magnitude, not frequency. So in an induction motor, if you change the voltage magnitude only, what is the problem with that? How many took 338? Okay, so good. So for induction motors, how do you control their speed? You've seen this curve for sure, right?
Yes.
This is the torque speed curve for the induction motor, or torque slip curve for the induction motor. And this is the maximum torque, starting torque, and this is your operating point for the induction motor probably, right? So if you would like to, this is your operating point, right? So if you would like to change this operating point to here, how would you do that? What would you change at the terminals of the motor?
The frequency of the input.
The voltage magnitude and frequency, not the frequency only. If you change the frequency only, or if you change, because if you remember, I'm sure Dr. Haytham derived it for you, and you will the V over F ratio is proportional to the flux inside the machine, right? So if you remember the derivations that Dr. Haytham went through, and then flux inside the machine is proportional to torque, right? So if you maintain the V over F ratio to be a certain value, which is suitable for that specific motor, then you can actually, what you can do is actually shift this whole curve to the left or to the right. I can do this. I can keep my same maximum torque, and then I can,
Which is the basis for
excuse me?
It's a basis for a control method.
Yes, so the V over F control method is, is the work. I mean, this is how you control induction motors. Fine, there are some, people came up with different names to control V over F in a nicer way, for example. But generally, it's all V over F at the end of the day, right? So we did that. We changed the speed, and we maintained maximum torque, and our starting torque was actually higher, right? That's if you do this V over F. But with AC voltage controllers, I can only change voltage magnitude, not frequency. So what will be the result? I cannot do this, obviously, right? I cannot do this. I cannot do this shift, right? Since my frequency will not change, then my slip, the point, this point, my maximum slip will not change as well, right? So instead of the curve doing this blue, the curves will start doing. If you remember, Dr. Haytham drew these for sure, right? So this is what happens if you only change the voltage as a magnitude, right? So if you change the voltage as a magnitude, fine, you can. It's not a way to control speed because your operating point is still around here, right? This is where your operating point is. So your slip range is very narrow. So it's not a way to control speed. But if you reduce the voltage that you apply to the motor, fine, you have an electrical circuit at the end of the day. You have a motor that has some, RL, blah, 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 right? If you reduce the voltage, what happens to the current? It's a passive circuit. If you reduce the voltage, the current will decrease. Right? So I will decrease the starting current. So if I have a circuit that I reduce the voltage, I will reduce the current, which is what we want to do with the starting case, right? So, but will it work with all up? But what happens when you reduce the voltage? When you reduce the voltage and maintain the same frequency, you reduce your starting torque and you reduce your breakdown torque or your peak torque, right? So if you have a load that is here, this is your load. At 0 speed, you have to supply a load, and at high speed, you have to supply a load. If this is your kind of load, can you do this? Or if this is your kind of load, what kind of load is this? I'm sure Dr. Haytham drew it as well. Proportional to speed squared. Dr. Haytham did not speak about loads that are proportional to speed squared. Okay, no, like fans or centrifugal pumps.
I don't remember that.
Okay, maybe it's fine. I'm sure he talked about constant loads or variable loads at some point. But regardless, so if you have a load that is like this, and a load of this nature is a centrifugal pump, because I think fine, a centrifugal pump is not going to be pumping a lot of fluid at 0 speed, right? You're going to start the pump, and when you start the pump, it will start pushing the fluid. So initially, there's no fluid to push, so there's no torque. So centrifugal pump can do this. A fan, same thing. Air is fluid, basically, right? So fine, you start your fan, it's not going to be cooling you instantly, right? It will take time for the air to reach you, which is being pushed by the fan, right? So same thing, fans don't require torque at 0 speed. But how about an elevator?
Yeah, because lots of
You don't want an elevator that at 0 speed it will fall down, right? So some loads you can, of course you can mechanically brake the elevator instead of electrically brake the elevator. But modern elevators are, they all require torque at 0 speed. So they would have a electrical brake or electrical control at 0 speed as well as a mechanical brake as a backup. Yeah. So some loads would allow for you to do this, some loads would not allow for you to do this. So if you want to limit your starting current, you would use a power converter that is going to change voltage only, and if your load allows it, you can do that. So a load like this would allow that. So you can use a soft starter in an application like this. So if you have a problem with motor starting in your facility, put a soft starter. This is like a workhorse. It's like the workhorse of the power electronics industry. You sell many of those. If you have one, if you can develop a product like that, you sell. Many of those you will sell, yes. Always people want to buy soft starters. So, but again, you have to understand your load, right? So you cannot just plug it in anywhere. So you will find, these you will find. And this is the topic that we will cover in point 6. So we will discuss how to design these converters. What do they look like? One way of designing these converters. Like you can remove what we've studied, put another type of converter that will also do the AC to AC conversion job, but more complicated, for example, more costly, etc., etc. So now we did what? We did the AC to DC, and then we did the AC to AC, right? The next family of converters we will study will be the DC to DC converter. So, these power banks that are used to charge your phone. The power bank is a battery, it's DC. Your phone is DC. You need something in there that's DC to DC. That's one thing, for example. one application of these of a DC to DC converter, for example. If you have a photovoltaic application, a photovoltaic panel produces DC at its output. If you want to use that only to charge a battery, it's a DC to DC application, right? If you're going to connect it to the grid, it's what? If you're going to take a photovoltaic panel and connect to the grid, then you require what kind of converter?
Converter.
That's the DC to AC. That's the last family of converters we will study. So we go through the AC to DC converters, AC to AC converters, and then DC to DC converters, and then the DC to AC converters, or what we call inverters in that case. So we will study all four. So these are the four kinds. There's nothing. I mean, these are all four. However, all four can be done in 100 ways. We will only study a few ways to do it. That are the basic ways to do that. And of course, while doing that, we said we will study the devices, and we will study, of course, the reactive element, the L's and C's required to make this happen. Because anytime you're converting power from one form to another, that means you have to, sort of have a place to store the power temporarily before converting it to something else. So typically, L's and C's are a good way to do that. So I would take the AC power, find a way to store it in a capacitor, store the energy in an inductor, and then take that energy and chop it up, for example. So we will spend some time on L's and C's in the class, and then of course you will see all of this stuff in the lab, and you will build, the main converters that we will discuss. You will build in the lab, look at the waveforms, simulate them, etc., etc. So that would be the main cross. I mean, this is what we will study in the course. Yeah. Any questions? Important stuff. Okay, so my office is here. It's 246G. I don't know what your schedules are, Mondays and Wednesdays. So what would be the best time for office hours, Mondays and Wednesdays? Morning. That's fine. So I'll change those. I'll change this to morning. So 9 o'clock maybe.
Yeah, around lunchtime also.
I have no problem, but sometimes we have faculty meetings during lunchtime. So it's a good excuse for me not to attend faculty meetings, because sometimes they're not as amusing as talking to students. But sometimes we have good lunches there. So a man has to feed himself. So yeah, I'll be typically it will be 9 to 11, 9 to 12 in the morning. So I'll change this to the morning. Yeah. Wissam, I'm sure you've worked with Wissam a lot before, so Wissam is available every single day from 11 to 12. he told me every day, so he's available every day for you. So the class website, we went through that. The grade distribution, so homeworks and quizzes, 10%. There will be no class project. I don't know. I didn't. Huh?
I was just going to tell you to cancel
the project. There's no project. I don't know. Sorry. I will remove it. Yeah. So there will be no project as such. We used to build the real power converter. But again, it's a lot of effort. So if you are interested in building a real power converter, but in the lab you have everything ready. You connect with banana plugs and stuff like that. You have some experience with building a power converter. You saw what it's like, right? So even though you built it and you think it works, it will explode in your face. And we had a lot of explosions before, so I think.
Did anyone die?
No, nobody died. Nobody died. Well, but Dr. Ziad's hand. You saw Dr. Ziad's hand?
Yeah, I was there.
Yeah, you were there.
It's burnt?
Yeah. So the power electronics. When I was working, I worked for Schlumberger for 7 years. I was developing power converters for oil and gas applications. Yeah, and I've seen a lot of explosions. I've seen, for example, I had a board one time that, all the devices on the board just flipped open at something. They just exploded open. Of course, you have to be. You have to try to make sure that you're doing the experiment safely, right? So you're doing it such that the devices don't explode in your face. For example, I had the board upside down, so the diodes were all pointing down, and it was screwed down to a heatsink. So I had no problem, but you hear the explosions here.
So, how about we build the projects and you test them?
It's a good, it's a good idea. But I do a lot of that in my lab anyway. If you want to visit our lab, in our research lab, that's what we do. But of course, the safety guys come after us and they want us to cover every capacitor and every wire. So it's, I mean, again, power electronics, there's a lot of devices exploding there. When you're developing the circuits, I mean, of course, at the end, everything is stable, but even though the circuits are simple, like this brushless DC motor drive, is it difficult? The circuit is simple. The circuit is simple.
If you have your sensors, it's simple.
Sure.
If you have your sensors.
But
Otherwise, you have to do some battery EMF stuff. It's not easy.
sure, if you're trying to do sensorless, but I'm talking about in general, power electronic circuits are simple circuits. Controlling them is not easy because, again, what you're doing is you have all these inductors and capacitors, right? These inductors and capacitors. Inductors, if you interrupt the current through an inductor abruptly, what happens? Voltage across an inductor is equal to L di by dt. So if you, by mistake, open up the path for current flowing through an inductor using your power electronic switch, and there's current flowing in here, what is going to be the voltage across the terminals of the inductor? Huh? Zero?
Should it stay the same?
No.
Or infinite?
Infinite. Yeah, we said you have current flowing in there, that's I. And then you bring I from a certain value to zero. Right? You bring it from a certain value to zero instantaneously by opening this switch. So what happens to your voltage regardless of the value of the inductor? I mean, big change in I in a very small amount of time, almost zero, which means that the voltage will be almost infinite. Right? So assuming you have anything here, that you're measuring the voltage across, the voltage will be infinite across the inductor. Anything you have around the inductor will explode, right? And so voltages will change abrupt changes in current will cause huge voltage spikes across an inductor. Abrupt changes in voltage will cause huge current spikes through a capacitor, right? So which means through your circuit. Right, so whenever you're working with power electronics, you end up having to make sure that you deal with these things properly. That's why you put sensors. When you put sensors in there, you know that you should not open up the switch, for example, when you have a high value of current in the inductor. You need to do something about it. Yeah. Find an alternative path for the current to conduct. And that's what we do in power electronics. So we always find alternative paths for the conduction of current. You can do that in power electronics, but you cannot do that in a power system, for example. The power system, you end up with, if you look at the website, I put a video here. And that's what happens when you open up an inductor. Right, this is just a disconnect switch. It's a disconnect switch. You had two contacts that had, that were connected, and then we opened them up. It's another one. Yeah, this is here's the one terminal of the switch, the other terminal of the switch, right? As soon as you open up, you have this arc developed, right? This is, it's because you have an inductive system. Remember, our power system looks like an inductor, right? People that took 459, your whole power system you can resemble as an inductor. So if you are going to open up your the disconnect switch that is feeding your power system, then it's basically opening up an inductive current. You open up inductive current, and between these two terminals that you've opened up, you have infinite voltage. Infinite voltage will break down the medium that's between these two contacts, right? Air breaks down at what voltage? 30 kilovolts per centimeter, right? So air breaks down 30 kilovolts per centimeter. So anytime but I'm telling you I have infinite voltage, theoretically speaking. So I'm breaking down that air. If I break down that air, I will have an arc. Now I keep opening up my terminals of this device, fine, the arc becomes longer, it sees more resistant. At some point you will quench the arc. but you need a huge amount of space. Or you put a circuit breaker. In a power system, of course, this is called an isolator. It's not a circuit breaker. So typically, you never actually open an isolator when the system is powered. Typically, you have a circuit breaker and an isolator. Because circuit breakers, the problem is people cannot see the terminals. If you're far away, if you're a maintenance guy, you're far away. I cannot look and tell you if the circuit is energized or not, if I only have a circuit breaker, right? But if I have an isolator, like a mechanical switch, just that it's in the open air, you can look and then you can know if the circuit is powered or not. If it's open, it's not powered. So circuit breakers are typically contained, right? They're typically contained in a gas-insulated chamber, or they're typically contained in a vacuum, so that they can quench the arc inside, right? So, or oil circuit breakers. So many different types of circuit breakers. So oil, air, vacuum, compressed air, gas-insulated. So all of these different breakers. They're used to quench this arc, right? But for you to know and see from far away, the people typically also have an isolator, or sometimes they call it a recloser in a power system. Yeah. So this is not a breaker. It's something that should not open on load, right? The breaker is supposed to handle that.
With an isolator, you still have a circuit breaker to quench the arc before you isolate?
Yeah. You typically use the circuit breaker to disconnect your circuit, and then you open up your isolator so that maintenance people know, from a safety perspective, you're okay. I know that the circuit is open here, right? Regardless, because maybe the circuit breaker indicator switch failed. You have a bulb there or a color or whatever when the switch is open or closed. Fine, maybe that fails, or maybe somebody broke it or whatever, right? So you still, voltages, you cannot fool around with them, right? Voltages and current will kill you. So safety is a very important issue that we have to make sure is designed within your system, right? Anyway, homeworks and quizzes. So we will, again, you will submit your homeworks. Wissam will just give you a grade for submitting the homework, and this homework has to be legitimate, meaning it's obvious that, like, for example, I can give you an example where people were exchanging homeworks, and the problem is they added a problem that was not in their homework, and a few people were doing the same thing. What does that mean? It didn't reflect. Fine, they either copied it, or fine, somebody actually told the people that it was the wrong homework, which means that other people didn't actually spend time to open up the assignment and look at the problem numbers, right? So we took stuff like that. If it's chicken scratching, if it's legitimate, looks like you put some effort, even if it's not correct, it's okay. You submit that, you'll get credit for it. And then you will be quizzed on the homework. So one of the problems in the homework that you had, you will get a quiz on it in the lab or in the class. It depends on how things work out, but typically it will be in the lab, yeah.
Sir, will the solution be posted before or after the quiz?
Now, typically after you submit, we will give you the solutions. I think you have a day. What did we do in 325? What did we do? Was it this? No, we gave it before. Solutions were given before, typically the quiz, yeah. So you will typically have the solutions before the quiz. So yeah, that will be 10%. I left it vague between homeworks and quizzes, so that I can punish you if I want to. I can make quizzes worth more. I can make homework worth more. No, I'm just kidding. So it will probably be so that I can help your grade. Yeah. So it's if I put 5% and 5%, then maybe 5% in the quizzes is too much because you didn't do so well, right? So I may shift it towards the homework or the quizzes, depending on how nice you are to me. Right? So, you got a question?
Is the final exam going to be cumulative?
The final exam going to be cumulative.
For now, at least.
For now, I'm not going to answer that question. Okay. I don't remember. I'll check what I did before. I don't think it was. But I will check what I did before. Yeah, I don't think it was.
Accordingly, we only have 5 labs. Does it mean that we have weeks off?
The weeks that you don't have lab, you will have recitation. So you will have recitation.
Usually it's like a week with lab and then a week
Yeah,
without.
week lab, week with recitation. So we'll go through that. So I'll go through the schedule, right? The lab schedule. So any questions on the grade distribution? Simple grade distribution. I guess there's no. I will determine the dates for the exams, and I'll put them on the lecture schedule soon. We talked about the homework policy. Again, I have no problem with you working together on the homework. Just don't copy. I mean, it's good to discuss. There's nothing wrong. I'm sure since they're from the textbook, you can come up with the solution manual online. It's better for you to solve them. Okay, I mean, because you will be quizzed on them. I think it's better for you to understand and solve the problems. Yeah. I think if you do that, you will do well in the class. I mean, people that took my class before, I think if you solved your homework and you understand it, you should be fine. Yeah. The lab schedule, so that we are covering that. So as we said, there will be a recitation between every lab probably. So the 1 week lab, 1 week recitation. So you can spend time in the lab solving problems, which will be helpful for you. So we will solve problems that if you have some homework problems that you had trouble with before, fine. Otherwise, there will be problems, practice problems. Yeah. So there, so 5 labs. So it's not too many labs, I would say. Any questions? No. That's this. I will add. I put the lecture schedule in there, but I put tentative exam dates, but I called it a draft here so that you don't hold me for it. So I put 2 exams here, and then the final will be somewhere after that.
In class?
The exams will be in class. Yes, the exams will be in class. 2 exams. So these are the 2 days, the 2 days a week that we have. 2 days a week, 24th, 29th. The 2 days that we have for lectures. I think I messed up on week 1. Yeah, sorry. I will modify the dates because the first week we only have 1 lecture. So, but the dates are correct. But this week is week 1 is only 1 lecture. Sorry. Anyway, this is a work in progress. The dates are correct, but I will modify this. But the exam dates are tentative. Okay, this is tentative exam dates. We'll work on it together.
So can we agree on them as a class, or you will determine them in
No, I will suggest, and I'm a dictator. I will say this is it. That being said, we can get started. We have 5 minutes. We can get started on.
Are you serious?
I'm very serious. I'm really serious. It's fun stuff. It's fun stuff.
Okay.
What? You thought we would stop?
I mean, 5 minutes, but
It's still an introduction, right? It's still an introduction. So, again, we talked about the 4 conversion technologies, right? So we said we have DC to DC, we have DC to AC, we have AC to AC, and we have what?
DC.
We have DC to AC,
Oh, no, AC to
AC to DC. Yes, sir.
I have a general question. What is the general efficiency on all of these 4?
No. So inside here, for example, you can plug a circuit that's 50% efficient, or you can plug a circuit that's 99% efficient.
Yeah, but I assume there's a theoretical limit.
No, theoretical limit is if you consider the switches are ideal, it's 100%, right? So, and that's the beauty of power electronics. So, if you think of your 325 material, and that's something I was going to do next class, right? If you think of your 325 material, okay, just quickly before. If you think of your 325 material, this is a MOSFET or a BJT or whatever, some device, MOSFET or BJT, does not matter. And I will not put in all the bias, with the MOSFET or BJT, you have to, put it, have DC operating point, AC operating point, etc. I will not draw all of these around it, but for now I will just say that I'm able to operate this device, right? If I operate this device the way you learned to operate it in 325, right? then if I have a 9-volt input and I would like a 3-volt output, right? What is the voltage across this device?
6 volts.
Exactly, 6 volts, right? So you have 6 volts across the device, and assuming this is 1 amp, what is the power loss in this device?
6 volts.
6 watts, right? So this is what we know how to do from studying 325. What we will do in this class, for example, is I will have very similar circuit, but I will operate the device very differently. So instead of operating the device in linear mode, like we were doing in 325, what I will do is I will keep chopping the input. So it's called pulse width modulation or PWM. So I will chop the input. So I will have this 9-volt input, same 9-volt input, and I will have the same device. But I will just operate the device in a different way, and I will have to put some sort of filtering stage between the input, before the output.
DAC?
The what?
DAC?
Not a digital analog converter. It's actually this filter behaves like a digital to analog converter, because actually before this filter, what's happening? I said that this switch is going to be opening and closing. So I'm going to be taking this 9 volts and chopping it up. So this is 0 to 9, 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 right? 0 to 9. If I, put a filter here, what am I going to do? Yeah, I will come up with the average value of this waveform, for example, right? This average value of this waveform is like converting from digital to analog, right? Because I had 0 to 9 or 0 to 1 if you were talking digital, and then I have now a constant waveform, or if I'm changing the width of this, then this thing will go, this red will go up or down depending on the width, right? So it's like converting from digital to analog, right? But it's not, basically what we're not really doing that. We are actually just filtering. So this will be, we will study lots of types of, different types of filters that we can plug in here, but you can put a capacitor alone, or you can put an inductor alone, or you can put an inductor and a capacitor together. We will study different types of filters and we'll see what we do. So to answer your question, I don't know, what was your question?
What efficiencies can I
What
expect?
efficiency? So yeah, good. So what is the efficiency here of this converter?
1/3.
1/3? How did you get that?
You're getting 3 volts out of 9 volts.
Why is that efficiency? مش فاهم. No, how did you come up with that? What's the efficient definition? What's the definition of efficiency?
Okay, so
Huh?
the power in and the power out, or the power out over power in.
Exactly. It's
Yeah.
power out
Power out.
over power in. That's efficiency, right? So what is the power out equal to?
3 volts.
3 volts times 1 amp, right? And then power in, 9 volts times 1 amp. It's a series circuit. So it's 1/3. So the efficiency of this thing is 33%. Right? 33%. We will, and I said that the theoretical efficiency of this thing is 100%. So which is better?
100%.
325 or 438? Anyway, we'll stop here, and next time we'll talk a little bit more about this. Yeah.
There's no, I have no idea. But I was